Okay, this is the Architecture 5327 Structures 2 lecture on Friday, October 2nd. I'm recording this, and if you look at the announcements, there'll be a link to this recording. I have a doctor's appointment tomorrow, which precludes me from chatting with you all about bolted connections, but undeterred, I will forge ahead, and we will talk about chapter 12 of the text, and it is the chapter on bolted connections. So we started on this chapter on Wednesday, and we got down to, wait for it, the types of the actual types of connections. Okay, so here's where we left off. It's section 12.5. So we can fasten or tighten the bolted connections, and there are three versions of connections, and actually the tightening of the nuts, and those are listed here one by one. And the value of the connection is based on whether it's a snug tight bolted connection, whether it's a pretension joint connection, or a slip critical bolt connection. So let's look at each one of those and we'll see what the difference is. The snug tight bolt connection is the tightness that would be produced when you and I take a wrench and we tighten the bolt all by ourselves. Okay, so if you're bigger than me, you may be able to tighten the bolt more than I do. Maybe not. So that's the most basic type of connecting, or the tightness of the bolted connection. If I'm building a 12-story building, I most likely don't want snug, tight bolted connections because of several things. The most important of which, I can't tell by looking at the bolted connection if the bolt is really tight or not. I'd have to go around and check every one. Additionally, the capacity of the connection is the lowest when it's only a snug tight connection. There's no friction resistance between the two members that you're bolting together, and therefore the capacity of the connection and shear and tension is reduced. So the snug tight bolts are good for lug nuts on the wheel of your car, and we'll leave it at that. In pretension joints, it says the bolts, when installed, are required to be tightened to 70% of the specified minimum tensile strength of the steel being bolted. Okay, these connections are generally required in seismic areas as well as for fatigue-loaded connections. So when I design a bridge, for instance, a structural steel bridge, I will specify a pretension joint connection so that the connection is tight enough. I don't need to worry about the fatigue of the impact loading over and over and over again. Then the second or the third main type of connections is called the slip critical joint connection. Supposedly, when you specify a slip critical connection, the bolts have to be tightened to their full tensile capacity. So the bolts are in full tension. The connection of the two plates, we're squeezing them together as best we can. This is the best connection that you can get. Um, in the snug tight connections, as it says here, there could be a little bit of slippage between the bolts and the plates being bolted together. Remember, it says, and this is important to remember, all the problems that you've been doing. When I said, hey, you're going to use 7/8 inch diameter bolts, well, that's fine, but you blew off the 7/8 and you said, hey, the hole will be an inch in diameter because the hole has to be bigger than the bolt. Well, if the hole has to be bigger than the bolt, then you're talking about the enormous forces involved in say a 12-story building and the connection between the steel beam and the column. I would prefer that connection not slip, that the two members, the beam and the column, the angle between them remain intact. I don't want any slippage in that connection. So when tightening the bolt to its full slip critical load, the bolt must be tightened by one of the following methods. So there's a method to the madness. There's actually a way you have to tighten the bolts. The first is called turn of the nut tightening. Enough bolts are brought to a snug tight condition to ensure that the parts are brought into good contact with each other. And again, that's key. I don't want the two plates that I'm bolting together to slip, so they need to be in good contact with each other. Then the remaining bolts are installed and all the bolts are additionally tightened 1/3 to 1 full turn. Well, you and I probably can't do that. I remember when my dad taught me, and I keep going back to changing wheels. Okay, I'm sorry. But when my dad taught me how to change the tire on a car, and I'd put the new tire on, and I'd take the lug nuts and I'd screw them on the spuds finger tight, and then I'd go around and I'd tighten them with the lug wrench. Well, he always said once I did that initial tightening, then I'd go around to each of the nuts and try to tighten them even more. So I would turn at least 1/3 of a turn to all of the nuts to make sure that they were tight. That's a turn of the nut tightening. Secondly is the calibrated wrench tightening. Most all steel erectors, they will carry calibrated wrenches. The calibrated wrenches, it used to be the calibrated wrench was just a wrench that had a dial on the end of the handle, and when you tightened the nut, you could look at the dial and you could check to make sure that the torque was the prescribed amount on the dial. Now most calibrated wrenches are digitally operated, and you put in a little data card like you put in your camera, and you go around tightening all the bolts, and then you take that data card back to the office and you read all of the results of the tightening of the bolts. Number 3, the alternate design bolt installation. Each bolt must develop a tension not less than 5% greater than the tension required in Table 5.2, and this procedure requires what are called load indicator. Wait for it. These are called load indicator bolts. Remember, I was showing you these yesterday. Wait, I got to go get this heavy thing again, so bear with me. I'm going to go get our bolted connection. Okay, I'm not going to take the time to unscrew the nut, but here's what, let me turn on the document reader here. Just a second, just a second. Okay, remember from yesterday, that's this bolt right here. Okay? It is, there's the nut, there's the bolt, and here is that fluted end of the bolt. And what happens is you take that fluted end of the bolt, and it actually comes off as you ratchet the nut in place. Let me get my picture of the nut up here. So as you ratchet the nut down, you can see that this fluted end comes off. So if I'm inspecting that bolt, if that end has twisted off, then the bolt is properly tightened. Now there's still, wait, there's more. There's a direct tension indicator tightening method. So here's the bolt, here's the nut, there's the bolt head, and in between the bolt head and the plates that we're bolting together is what's called a load indicator washer. Aha! Do I know what a load indicator washer looks like? You bet you know what I do. Okay? Down here at the bottom, let me turn this thing over. Okay, I'm going to maneuver this so you can see it on the document reader if I didn't knock it off the table. Okay, this bolt right here, this is underneath this bolt. Let me turn this so you can see it better. Underneath this bolt is what's called a load indicator washer. Now watch this as I take this bolt off. As I take this bolt off, wait for it. Okay, here's that magic washer, and it is a magic washer. See, it's got dimples on it, all right? And those dimples are of a particular size, and they go like that on the bolt. And then when I tighten them down, when I tighten the nut down, then I've squeezed that load indicator bolt washer so that I can measure to see. There we go. So I can measure to see if the bolt has been tightened. So I actually squeeze this gap down. So when I squeeze and smush that smush is an engineering term. When I smush that washer, then I take a feeler gauge and I check to make sure that I've smushed the washer enough to indicate that the bolt has been tightened. So that gap might be, say, 25 mils. That's the size of the hickey on the washer. Then I tighten it down. It doesn't matter what I tighten it with. I could tighten it with just a plain wrench or a spud wrench or an impact wrench or whatever I want to do. But when I tighten it enough that that gap reduces and say to 15 mils like this, then I've tightened the nut. I measure that gap with what's called a feeler gauge, and a feeler gauge is just most steel erectors carry a feeler gauge, and it's just a bunch of very thin pieces of metal, the metal plate that are on a ring. They're about the thickness of the thickest one might be as thick as a knife blade, and then they get thinner and thinner and thinner down to the point where they're not much thicker than a piece of paper. And each one has a number on it, and what you slide varying thicknesses of those plates in that gap, and when you get one that fits snug, then that's the measurement. For those of you that have changed the spark plugs in your car, and I'm sure that's the majority of you, when you put the spark plugs in, one of the first things you do is you gap the plugs, which means you check with a feeler gauge to see what the distance is between the spark element in the plug and the coil the coil that turns and comes underneath that spark element. That gap in between, you measure with a feeler gauge. Okay. So those are the methods involved with regard to the tightening of the bolts. Now let's look and see how that plays into the design of the bolted connection. Okay, when high-strength bolts are fully tensioned, they clamp the connected parts tightly together, resulting in a connection that resists slippage. So that's what we've been talking about. If the shear load at the connection is less than the frictional resistance, what's the frictional resistance? Well, that depends on the surface of the plates that are being bolted together. The resistance is equal to the clamping force times the coefficient of friction of the materials. And don't worry, we're going to be able to tell what that is. So if the shear load, and so far that's all we've been looking at is shear load, when we bolt the two plates together, just like the problem on your exam, and when you calculate the capacity of the plates under the net tensile fracture, which is through one of the holes of the connection, or for you it's through path, what is it, ABGH, something like that. And you come up with that piece of T, that tension capacity. When you come up with that tensile capacity, then that's the shear load. If that shear load exceeds the resistance of the connection, then you need a bigger bolt, or you need to tighten the bolt more. So if the shear load at the connection is less than the frictional resistance, the connection is slip resistant. If the shear load at the connection is greater than the frictional resistance, the members will slip on each other and the bolts will shear. This is called a bearing type connection. So we need to remember bearing type connection and slip resistant connections. So What's the capacity of a bolt? Well, the capacity of bolt in single shear is R sub y, that's the load carrying capacity, is equal to A sub B times F sub B. A sub B would be the area of the bolt. F sub B would be the shear, the allowable shear stress in the bolt. Okay, so that's the capacity of a single bolt. Now we'll move down here to, before we can design the bolted connection, there are some spacing requirements. Specification J3.3 provides a minimum center-to-center distance for standard oversized or slotted holes or standard oversized or slotted holes. The minimum center-to-center distance should not be less than 2 2/3 diameters. So that's the center-to-center distance. If you got 1-inch diameter bolts, then those bolts need to be spaced a minimum of 2 2/3 inches apart, center to center. So you can't put the bolts really close together. That doesn't work. Minimum edge distances. The minimum edge distance of the plates is 1.5 to 2 times the bolt diameter. So again, if I have 1-inch diameter bolts, I can't get that bolt closer than 1.5 inches to the edge of the plate. That's from edge to edge. And then the maximum edge distance, the LRFD maximum permissible edge distance is 12 times the thickness of the connected part, but not more than 6 inches. So there is a maximum that you can be from the edge of the plates that you're bolting together. All right, for bearing type connections, go back to chapter 2 and look at the end of chapter 2, or maybe at the end of chapter 1, I forget. No, I think it's at the end of chapter 2, where we had that table that had the phi values, the resistance values. We looked for it last time we found it. I think it was at the end of chapter 2. The phi value for bearing type connections in single shear, phi is equal to 0.75. Then the shear strength of the connections, if you have a bearing type connection, which means that, remember that means that the shear load at the connection is greater than the frictional resistance. That means it's like having the two plates coated with Teflon, okay? And they'll slide on each other. So now, if I bolt those two pieces together and they got Teflon on them, and I tighten the bolt down and I apply tension to the plates, when I apply the tension to the plates, then the only thing that resists that tension is the shear capacity of the bolt. All right? So that's the shear strength of the bolt. For bearing type connections, it's assumed that the loads to be transferred are larger than the frictional resistance, will result in the bolts slipping on each other, putting the bolts in shear and in bearing. The design or LRFD strength of a bolt in single shear equals phi times the nominal shearing strength of the bolt in KSI times its cross-sectional area. That makes sense. So the phi value, again, I said is 0.75. For high-strength bolts, the nominal shear strength of the bolts and rivets are given in table 12.5 in the AISC manual. For A325 bolts, the values are 54 KSI if the threads are not excluded from the shear planes, and 68 KSI if the threads are excluded from the shear planes. Geez, another rule, okay? What that rule means, why would there be a difference in the shear strength of a bolt? You know, it is what it is, right? Well, that's wrong, okay? if the bolt, I'm going to go, when I make that horrible noise, I'm lifting up that bolted connection thing, okay? Let me get another bolt out of here that shows this a little bit better. Yeah, here we go. Okay, there are two dimensions to note in a bolt. Right, I'm getting organized here. Let me get the document reader up. Okay, so here is the bolt, okay? And what this says is that there are two different values for the shear of that bolt. Well, if the shear plane falls where the threads are, notice that if I measure the depth of the threaded part, that I've taken the overall shaft dimension of the bolt, and I've taken, at one time this bolt was just a smooth shaft of steel. Then I put it through a press, and I put these threads on. The threads are at the same location. The face, the outside edge of the threads, and the shaft are in a straight line. Okay, so that's a smooth straight line right there. But the dimension to the bottom of the thread, now that shaft size has been reduced because we've cut the threads out of the bolt. Aha. So that's why now we have two categories of bolts, and before you can design the bolted connection, you got to know if the bolts are included, if the threads are included in the shear plane, or if they're not, or if they're excluded from the shear plane. Okay, so that's part of the problem. Right, I'm getting that back up again. For A325 bolts, the values are 54 KSI if the threads are not excluded. Isn't that a double negative? If they're not excluded, then the threads are included from the shear planes. And 68 KSI if the threads are excluded. So the lower value would be the value of the shear strength of the bolt at the bottom of the threads where the shaft is actually smaller. Okay, for 490 bolts, A490 bolts, the values are 68 and 84 KSI. If the bolt is in double shear, its shear strength is considered to be twice its single shear value. Hey, that's pretty good. So if I'm shearing the bolt twice, okay, its shear strength is considered to be twice as much as the single shear value. The single shear value means that this bolt doesn't care how many times it gets sheared, because if there are two shear planes going through the bolt doesn't know that there are two different shear planes. It resists the shear on each and every shear plane that exists down the shaft of the bolt, and it could be 2 or it could be 20, and still the shear strength is the same. Okay, so the shear strength at each shear plane is X. If there are two shear planes, then the shear of the bolt is considered to be 2X. Okay, all right. So here's table 3.2, and this is what we've been referring to in the text thus far. This table tells us what we need to know about the bolts. The first column is the bolt, okay, and there were questions that arose for when you looked in table 7.2 at the bolt diameters. Also in there it said it depends on whether your bolt is group A or group B or group C, okay? And I think down here at the bottom, um, these are the footnotes that apply to these two columns, but notice that group A is when the threads are not excluded from the shear plane or excluded from the shear plane. Two values for the tensile strength and the values for the shear strength vary depending on whether the threads are not excluded or are excluded. Then for the group B, there are similar values. The group B are the A490 bolts, okay? So the A490 bolts here, the values for not excluded and the threads excluded from the shear planes. Notice that the tensile strength, it doesn't make any difference, okay? The threads don't play into the nominal tensile strength. The tensile strength is what it is. Group C is a different type of bolts, F3043 bolt assemblies, and we're not going to address those particular types of bolts. We're doing A325s and A490s, and there is the whole of table J3.2. So we now know what value to use when calculating the tensile strength of the bolt, and we know what value to use when we're calculating the shear strength of the bolt in a bearing type connection. Okay. So here is the bearing strength of a bolt, and we'll do an example problem right there. Okay. So the bearing design strength of the bolt equals phi, which is 0.75, times the nominal bearing strength of the connected part. So here R sub n is the bearing strength of the connected part. 1.2 is a constant. Initially, what it means is the bearing strength of the connected part has to equal 1.2 times L sub C, which is the distance to the nearest bolt hole, times T, which is the thickness of the thinnest member to be connected, and F sub U, which is the ultimate design strength, tensile strength of the bolts, which is given right here. There's the ultimate tensile strength of the bolt. Okay. So there's the equation. That value has to be less than 2.4 times the diameter of the bolt times the thickness of the plate being bolted, the thinnest plate times F sub U. Let's do an example. Here's example 12-1. Determine the design strength, P sub C times P sub N. That's the nominal strength for the bearing type connection shown below. The bearing type connection, that's important. They're the two plates. They're half-inch plates. The steel is A36. A36 is the common steel strength for plates and angles. F sub Y. F sub U is 58 KSI. Remember, it could vary from 58 to 80, but we take the 58. The bolts are 7/8 inch diameter. They're 7/8 inch diameter A325 bolts. They're in standard size holes, and the threads are excluded from the shear plane. Let's see if we can determine the design strength now of this connection. So this is similar to what we've been doing before, okay? If we determine the design strength of this connection without considering the bolts, we would first take the gross area, which is a plane in between the bolts, and we calculate the nominal strength based on the gross area. Then for this connection, for the tensile net area, we would take, say, a path from here to the center of this bolt, and maybe diagonally to the center of this bolt and the outside. So we have to find the effective area. There's no U factor because they're plates, but there would be an S squared over 4G factor that we'd add back into the net area to get the effective net area. Then we do the block shear, and maybe the block shear would go from this hole to the edge of the plate and down, so that would be the block shear. And all three of those calculations are based on the sizes of the holes and have nothing to do with the bolts. So now we're going to do a fourth calculation. How much load will the bolts carry? They're 7/8 inch diameter bolts. If you went to table 7.2, you'd see that these bolts are 0.6 square inches each. That's the area of the bolt. And here's how we'll do the calculation. Just like I was saying, on the gross yielding of the section, there's 36 KSI. The plates are 12 by a half inch. 216, multiply that times phi, 194.4. So that is based on the gross section yielding of the plates. Remember that number. Now, the tensile rupture strength is the gross area minus two holes. So we actually took the two holes in a straight line, that there are two 1 inch diameter holes times a half inch for the plate. U is 1 for a plate. So we get the effective area is 5 square inches. That times 58 KSI multiplied by 0.75 gives us 217.5 kips. So that value is greater than the gross section yielding. So thus far, the maximum load the connection could carry is 194.4 kips. Now we'll do the bearing strength of the bolts by the equation that we just went through. We need L sub C to plug into this equation, and L sub C is the lesser of, let's go back up to where it describes L sub C, the lesser of the distance from the edge of the plate to the edge of the nearest hole, or the clear distance between the closest holes in the direction of the load. So that 3-inch dimension from the edge of the plate to the center of the first hole, that minus a half an inch would be the distance from the edge of the plate to the edge of the nearest hole. Then the clear distance between the closest holes would be 3 inches less a half an inch and a half an inch. So it would be 3 inches less an inch, or 2 inches. So there's the calculation. It has to be the lesser of those, so the 2 inches controls. So now we're ready to plug and play in that equation, or in the inequality. 1.2 is a constant. L sub C is 2 inches from what we just surmised. Then the 1/2 is the thickness of the plates, F sub u is 58 KSI, and we're going to multiply that times the number of bolts. We get to count all of the bolts in the bearing strength calculation because all of the bolts will be in shear. So we're going to multiply that times 4 because we got 4 bolts. Okay? So in this equation up here, this is for 1 bolt. All right? We got 4 bolts. You have to multiply this first part by 4. So we did that. We put in the number of bolts. We checked the inequality. And the inequality is 2.4 times D, which is 7/8 of an inch, times T, which is a half an inch. F sub u is 58 KSI. The number of bolts is 4. So that's 243.6. And according to this, the value, we have to take the smaller of those values. So the 243.6 controls. The phi value is 0.75. 0.75 times 243 gives us 182.7. Remember that number. Then here's the actual shearing strength of the bolts. That is the shear strength of the bolt times the area of the bolt times the number of bolts. So there's 68 KSI is S sub n V, the shear strength of and it said in the problem that these are A325 bolts. So we go up here, what is the nominal shear strength of an A325 bolt? And the threads are excluded from the shear plane, 54 KSI. If they're included from the shear plane, it would be 68. So we use 68 because the threads are included in the shear plane. There's the area of the bolt, 4 bolts, 163.2 times 0.75 gives us 122.4, and we're done. That's the capacity, that's the shear strength of the bolts. So now we have done the bearing strength capacity of the bolts is 182. The shear strength of the 4 bolts is 122. The based on the tensile rupture strength is 217, and the gross yielding is 194. The lowest of those 4 values controls, so at 122.4 kips, this connection would fail. The bolts would shear. So now you can see, now we've filled in those holes from chapters 3 and 4 with bolts from chapter 12, so we can see really what the capacity of the connection is. Okay. So that will conclude. We have another example to do, and there are a couple homework problems I'll post to the Canvas today. So that concludes the lecture for today. As I said, this is recorded, so I will stop the recording. The recording will be saved to Microsoft Stream, and there will be a link to the recording, and under the announcements, I will paste that link in so you can click on that link and listen to the lecture. So that will do it for today. We'll stop the recording, and we'll actually talk to you all on Monday.